Going to do a nice electrical calculation with the sys parser. Let me just take the recording out of the way. So we have an oscillator with an output voltage as 9 volts. So VO equals 9V or 9 volt. The frequency of the oscillator is 1 megahertz. The J is the square root of -1, so it's just the JW is angular velocity in radians per second. JW is J, that is equal to the square root of -1 times 2 pi times the frequency of 1 megahertz. We specify a lagging current through the impedance that we want to calculate of 1 minus 30 degree milliamp. Now that 30 degrees is lagging, meaning we are working with an inductor of a certain Henry value in series with a resistor R. So now we're going to calculate the Z, or the impedance. Now Z is the output voltage of the oscillator VO divided by the current I, that 1 minus 30 degrees milliamp. So that gives you the Z, or the impedance. So it's basically voltage over current equals resistance or impedance. Now impedance is not exactly the same in resistance. It can be a resistance, but it has a phase angle, so it's a complex value. Now the power factor is a cosine of the angle of the impedance Z, and the reactance of L, XL, is J times the Y component of the impedance Z. So that is reactance of the coil is J, or square root of -1 times the Y component of, or the Y of the impedance Z. Now the resistance R is equal to the X component of, or the X of the impedance Z. The coil L is equal to the reactance of L, XL, divided by the complex angular velocity, JW. So L is equal to XL divided by JW, and JW is determined by the frequency. JW is angular velocity, but times J. Now, just to show you that the square root of -1 and 1 to the power of a half and I and J is equivalent values. So I just added that part. So now we're going to set the default complex number mode to degrees mode, and we're going to select everything, and we're going to evaluate, and I'm going to drop down the report, and you can see the full calculation there for yourself in polar mode, polar degrees mode. So we have our output voltage is 9 volt, our frequency is 1 megahertz, our angular velocity times J is J angular velocity. There's a value in radians per second, and it's got a 90 degrees phase angle because we've multiplied by J. The current, it's interesting the way the parser represents complex, like negative degrees causes normally a negative number with a positive angle of 0 to just before 180 degrees. So that's the way the parser represents. So even if this has a negative value, it doesn't mean it means negative. It's in the opposite direction basically. You see that is -30 degrees. and minus or 180 degrees minus 30 degrees is 150 degrees. So that vector is just that minus sign means it's in the opposite direction of the positive vector of one angle 150 degrees is exactly equal to one angle minus 30 degrees. So the parser just represent a complex value in that way with a phase angle, because that's a way I integrate negative and positive values, and I had to do it like this. Okay, so don't worry too much, but just understand that if you have a negative phase angle of minus phase angle between 0 degree, just over 0 degrees, and smaller than 180 degrees, you will get a negative value because it will be in the opposite direction. That is a negative sign of the positive phase of one angle around 50 degrees. So these two vectors are exactly the same value. Okay, so the impedance Z is the output voltage of 9 volt divided by the current with a negative phase angle of minus 30 degrees, and it gives you 9 angle 30 degrees kilo ohm. The power factor is a cosine of the angle of Z, or the impedance. So there's a cos phi, or cos of the angle of the impedance, and that is the power factor. The XL value, the reactance of the coil, is J times the Y component of Z. Now, Y of always gives you a value on the x-axis, but because XL is imaginary, we must multiply it by J or I. You can use I also, but in electrical engineering we use a J, because a small lowercase I can denote instantaneous current. We use I for current, and a small lowercase I can be very confusing in electrical engineering. So the J is preferred to denote the square root of -1, and so that is just a square. Say it's on the y-axis, and then we multiply that with the y component of the impedance Z, and then we get that complex or y component, a y-axis value of 4.5 on the y-axis kilo ohm. If it was a negative value, it would just mean, with the same angle there, it would just mean if there was a minus before the 4.5, it would mean that XL would have been on the negative y-axis in kilo ohm units. So we can do complex units, as you can see. Now, R, the resistance, is an X component of, or the real component of, the impedance Z, and that is the kilo ohm value. And when we do it in rectangular mode, and I'm going to do the same calculation in rectangular mode also, and just show it to you, you would see that that would be the same than the X component. It's just the X component of the impedance. But now we are in angular mode. It's not so clear. If you look at Z, you must look back at Z. You can't see the X and Y components. You only see the radius and the angle here. But when we do it in that mode, there, you will see it's in the XY component form. That's what's so nice about the parser. You can output your values in any complex number mode. Now, this is for outputted values, so the way it will output values in complex mode. But because the type SE values is complex with units, you can see you can do complex mode calculations just as easy as simplex mode calculations. Now, you don't have to set modes for simplex and complex modes on the sys parser, because I've fully integrated complex number mode with simplex number mode. So you basically just type it, and you can be in any default complex number mode. Internally, it doesn't matter which mode you are in. Internally, the calculations will be correct. and you can just output it in the form you like it. If you want radius angle, then you go for these 4 modes, because you can select the kind of angle you want. This is for radius angle, and if you want, here you can have your raised separates with the x and y components of the unit vector. Uh, that assume a unit vector, that part in parentheses, and that's a radius that will normally be for the angle. Uh, and that second mode will give you the complete x and the complete y. You basically can ignore that 1 before it. That is just a scalar, and it's always 1 in this mode. So it's just the x and y coordinate basically that you get in this mode. And and there I calculate the R value, and then I calculate the L, the coil's value, and you will see it will give it in microhenry. I haven't told this in this modeling. I haven't told it the units of the coil. It actually computed that the coil L, if you divide XL with JW, you will get it in microhenry, and that is the correct value of the coil in series with this resistor. So if you have this resistor and that coil value, you will get a phase angle I of 1 minus 30 degrees milliamp. So basically I use the current, I've prescribed the current, and then I calculate the value of R and L basically, and also the power factor. So here you can see the full calculation. It was very simple. Here I just demonstrate that square root of -1 is 1 angle 90 degrees, -1 to the power of a half is also angle 190 degrees in this mode, of course, in this degrees mode. There, you see there, and you see that I is the same value than square root of -1, and J also. So you now know the meaning of these things. These are all the same value. So you can see that I've used that J value there. JW is J 2 pi F, 2 pi times the frequency. You can see there, and you see J, Y of Z there. So let's do this calculation now in radians mode. So I'm going to clear this. You must just like pause and study, and then I'm going to clear this, and we're going to do it in angular mode, in that last mode there. Okay, so I've done it now in degrees mode, and we're going to do it in that mode. So let's clear it and redo it, reevaluate it. So I've cleared it. I set the mode now to IXA mode, and make sure it's selected. Just make sure, you see, and I evaluate it, and you will see the values has changed now in rectangular mode. And so it's now XY values instead of radius angle values. So we still have our VO is 9 volt, our output voltage of our 1 megahertz oscillator. Our frequency is 1 megahertz. Angular velocity is a complex, obviously, because we have got that J there, 2 pi F, and that is in radians per second, and that's an X component, comma, and the Y component. You see, dot is used for separate the integer from the fractional part, but comma is used to separate arguments with the sys parser. So that's a standard that I use. That's always like that. That's just a syntax. So the current, I specified, I want 1 milliamp, with a phase angle of minus 30 degrees. Now that 30 degrees, you must understand that is a unit vector phase angle, and you multiply the unit vector. That minus 30 degrees is already a unit vector angled as basically one angled by minus 30 degrees. That's why it's underscore degrees, means it's a unit vector angled at 30 degrees, and you multiply it by 1 milliampere. So all these things are just chain multiply. Basically, between that 1 and the parentheses, there's an assumed multiplication. So it's 1 times in parentheses minus 30 degrees That is a unit vector angled at by minus 50 degrees times milliampere. So you must understand, if you use the PEMDAS rules and you want to make sure a value is like, if you use the vision and you want that value as a whole to be multiplied out, it's best to put it in parentheses, um, especially after a division sign, because the PEMDAS rule will interfere and will actually only if you say 1 divided by this thing, it will be 1 divided by 1 times that. So you must put this whole value in parentheses if it's below the line and you want the full thing below the division line, so as a divisor. Okay, so just a note, and then that is one, you can ignore the one, you know that. That is the x component, 0.8660, and then you have a comma, and that's a y component of minus zero point 0.5 on the y-axis, close parenthesis, milliampere. So this is a radius of 1, but it's always assumed 1 when you are on IXA mode, you see? 1 xy, you see it here. 1 x component, comma, y component, kilo ohm. That's the impedance that I've calculated of I. You see, I've used I and VO, and then I've calculated Z from that, VO over I, and it gives me in a rectangular mode now. Now the power factor is the same. It's the same formula as in before. It's just now in rectangular mode. It's a cos of the angle of Z, and that is just a simple value. So it's got a zero phase angle because it's just a power factor. So you see the calculator knows exactly where we are with simplex and complex values. You don't have to have different modes for simplex numbers and or values and complex numbers. It's fully integrated with type AC values. That's the power of type AC values. It really works. You see, it makes your calculation so much easier. It actually knows when the answer must be a simplex number. You just get your formulas right. XL, the reactance of the coil, or the inductor, basically. The L value is inductor. We have an inductor in series with a resistance. So X, we normally, if it's a capacitor, we would say X and the small c, or a lowercase c. But in this case, it's a X, a capital X, and a lowercase l. So that's not a 1, that's a L. It's J times the y component of, that is always the simplest value of z. So we multiply it because xl is on the y-axis. So that you can see it there, the radius 1 you can ignore, not x component, that is a comma, not a dot. So it's not comma 4.5 on the y-axis kilo ohm. So it's on the positive y-axis, the XL value. It's 4.5 on the y-axis kilo ohm, basically. That naught is on the x component is 0. There's no real component. There's an imaginary component of 4.5 kilo ohm on the positive y-axis because the sign is positive there. It's 4.5, not negative 4.5 on the y component. You see the comma is a separator there between x and y, and the radius assume 1 in IXA mode. So that is also correctly represented by the parser. The resistor R is a x component or real component of Z. Simple. At 7.7 kilo ohm as before, and it knows it's a simplex number. L, this is a coil value, the value of the coil or the inductor in Henry. We always, especially for like a capacitor, is always farad or like micro or millifarad. That is just a prefix, but in this case, L is XL over divided by the complex angular velocity. That's always on the J2 pi f, you see there. So that's XL, that is y, or the Jy of Z, divided by 2 pi J2 pi FL, 2 pi f, sorry, not the L. If you see XL is J2 pi FL. 2 pi frequency is JW. or J2 pi frequency is JW, and L is your coil value. But if you reverse, change the subject of the formula, L is equal to XL divided by JW, and that gives and the Parser know the units, you'll see now, of 716.197 whatever micro Henry. Now that's very smart. The Parser doesn't only know the unit is Henry, it also knows that you should scale it to the micro Henries due to the size of the value, and it will give. You can switch this off. There's obviously settings here that you can control if you want base units or high units, and you can also disable this automatic unit prefixing. So the parser has automatically calculate that microhenry unit and the correct value in front of it scale to microhenries. And there was no place in, and I will show you the valid source code that I actually told the parser that should be microhenries. And the same with many of the kilo ohm also was calculated. You see, it's not only ohm, it's kilo ohm. So the parser is smart enough to know the unit only from the formula. So you don't have to do any unit conversions in your formulas. It's all done automatically for you. The angles is handled automatically, and the conversion from rectangular of polar to rectangular is handled automatically. You see minus 30 degrees, and it converts it to an x component and a y component. You see there, it's minus 0.5 a y component, and that is a x component, and in also unit is milliamp. I haven't specified because the things that I've specified, I will show you, is only this. This is all the formulas. There's no unit specified. You can look through it. You see that last one is just to show that the square root of minus 1 and minus 1 to the power of half and I and j is exactly the same value. And you can see it here. Square root of minus 1 is 1 times x0 y1, same value 1 times x0 y1, same with I 1 times, and that 1 you can ignore. There's basically coordinate from the 0 to 0 comma 1, 0 comma 0 to 0 comma 1. That is a vector, and you see it's all the same. So I is exactly equal to the square root of minus 1, and even in rectangular mode. And yeah, you can pause it and study it. It's very simple. It's all here. And I'm gonna just go back to the. You can't fit everything in here, but the source equations is just a simple source equations. Yeah, so you can study the upper part, and then I'm gonna pull it down, and you can study the source equations. But there's nothing to it. Basically, you see them all. You see the last one is only that square root of minus 1 and the I and j. So I can just pull it up and just study the whole thing. It's all here, basically. All the formulas that matters to the electrical calculation is here. Okay, my friends, I hope you enjoyed this. This is interesting. The power of type SE values implemented in the CISC parser. I've written the software. It works very well. It might have a bug or two, but it's quite good. And all I need to update basically is this help files and things. But the code works, and the program is fairly ready for people to use. So I'm willing to share it with my friends, but I should actually get paid for this because really it's not thousands and tens of thousands of hours. It's like more than hundreds of thousands of hours of coding and developing that went into this. Maybe I'm a bit stupid, man. I don't know, but I've tried my best, and I've built this whole thing from the ground up. I had no help except for obviously Delphi that helped me a lot. It's an old Delphi version, Delphi 7, that I got from a friend of mine. But I'm not into making money. I just want to show the world a better way of calculating. And type issue values really does it because it's much more powerful than numbers. As you can see, you can really do complex number mode calculations We have coils, In a coil, the current always leads a pure coil inductor. That X value and the L value, that's to do with the coil. There's XL, that's basically the resistance of the coil to the AC, the 1 megahertz 9 volt AC supply. That is basically your resistance of the, but it's imaginary value. It doesn't give off heat because it's not on the real plane. It's on the y-axis, and that no, sorry, that's R. I'm talking about XL here. You will see it's 4.5 kilo ohm on the y-axis. Is 0.4.5, and that means it's his imaginary resistance basically, or a reactance we call it. You see, R is a real value. That's on a real plane because it's on an X off, and that is on a Y off. So this is your real thing that will give off heat. So you will get, you can calculate the power, it's easy. It's a simple real calculation. I haven't done it yet, but obviously the power can be calculated from the voltage and the current and the resistance. Or you can get the wattage or milliwatt, microwatt, whatever watts is involved here, but you can get the heating effect on the resistance. But L doesn't give off heat if it's a pure inductor. But the current through inductor will lead, uh, now the current will lag. We have a lagging power factor because if we have a minus 30-degree phase angle overall, you see there, and that means the current lag by 90 degrees through the inductor, the voltage. The current is 90, the wave of the current wave. You see, this is an AC circuit, so we have a 1 megahertz frequency. The current wave will lag the sine wave of the voltage by 90 degrees. The current wave will be something like sin angle minus 90 degrees, something like that. So the current lags by 90 degrees only through the L part, but we have a resistance of series with it. So the combined value of R and L or XL is that Z value. See that? That's impedance. Z is impedance. The letter for impedance is Z. That's a combined value of the resistor and the coil, the combined resistance. And X is purely the coil's effect, component of that resistance, and R is a real component, or the resistor. A resistor is also always real. It has no phase angle. The voltage is in phase with the current, or the current is in phase with the voltage basically. The voltage always, we assume a zero phase angle on the voltage, and the phase angle is always given on the current in electrical engineering normally. Okay, I hope you've enjoyed it. I've talked a lot. I had to explain things. So this is a bit of a high level electrical calculation, but it's a kind of things that you will do if you study electrical engineering, especially you don't use transistors and things like that. Yeah, it's more to do with coils, capacitors, and resistors. If you have them, networks works of them for like in radios or tuners and things like that, how to calculate those impedances and how to get the values of the coil or the capacitor. You can reverse engineer it, as you can see. You just need to change the subjects of the formula. With type SE values, it's a dream. Really, with a normal calculation, this calculation would have been a real pain. A real pain. With this calculator, it's basically a walk in the park. So I'm going to stop the video now, and I hope you enjoyed this. I hope you understand. Basically, what I did is I've given the voltage of the oscillator, I've given the frequency of the oscillator, and I've prescribed the current with a lagging phase angle of minus 50 degrees. Obviously, that is converted to a positive angle with a negative value, but doesn't mean it's actually a negative current. It just means in the opposite direction of that vector. So minus 1 in front of a value like this will mean, and with a positive angle will mean only in the opposite direction of, or it can be, meaning it can have a lagging phase angle. So normally when you have negative angles, you will have a positive vector with a negative sign in front of it. It's just a way the parser represents complex numbers in degrees mode. You see. So I'm going to switch it back to degrees mode just to make it interesting and give that form of the calculation again to you. Okay. So let's do it in degrees mode again. There it is. Drop it down and you can start it. I'm just going to show you, mention another thing before I stop the video. You see there, you can study it again for yourself. Okay, and I'm going to kill that. I can I can kill this whole thing, or I can just clear it. But the thing is, let's kill that. And another feature I want to show you is, you see if I've checked these values, all the variables that I want to be monitored. I'm calling it the monitor function. It's a very nice function. You can just check them, you know. It's not much to it. You just check that check boxes, uncheck or check. If you check them, and you can either hit this button or hit evaluate or enter, you would see your variables listed with the values there. You see, that can nice. So it's all together there for you, and you will see all your output value, final values there. So that's a nice way to monitor variables. If they have, especially if in rectangular mode, if you know you've got your x component and your y component, it can become times very long values, and it might not fit into your report. But because this has a small case, you will generally be able to see it in your monitor list box. So this is a monitor list box. So this is just a thing that I used to record this video with. Okay, so don't worry about that thing. I'm going to stop the video now by hitting that button. I hope you enjoyed it. And you would see that this parser really deserves respect, because really calculating with type SE values is so much better than calculating yeah, with floating point numbers. It's just, of course, type SE values include floating point numbers, but it's just more advanced type of data, you see, and it makes this kind of calculation so much easier. So I fully unified simplex values with complex number values with units, and you see the units. Plus, I do the unit prefixes. It's all the powers that type AC values can give you, and this pass is just implementation or a test bench to show you what can be done. Okay, I hope you enjoy it. Have a lovely day. Bye. Let's